Dear friends, today we'll have a discussion on multiple integrals. You know how important the definite integral is. I will first give you a brief introduction of the one variable definite integral before taking you to the multiple integral area. All of us know integral a to b f of x dx represents a definite integral within the limits a to b. Now, if f of x is greater than 0, we can interpret the definite integral as area. That is because if you have y is equal to f of x from a to b, then the whole area under the region is the sum of all such strips whose width is delta x, and this height is f of x. So this would be representing the area of a small elementary rectangle. So the area of this is f of x into delta x. So when you have many such strips between the range a to b, that represents this definite integral. Therefore, one of the interpretations of the definite integral f of x dx from a to b is area. But it is not always necessary that we think of the definite integral as an area. There are other possibilities. For example, f of x could represent arc length, or we can use it to find the surface area, or we could find the moment of inertia, we can find the mass, but it all depends upon how we interpret f of x and understand its nature. For example, when f of x happens to be mass, density, when f of x happens to be density, then the interpretation of this definite integral would be something. For example, it could be the mass. So the interpretation of f of x will decide the output of this particular integral. As a very simple case, we can visualize integral f of x dx from a to b as area of a plane lamina which is in the xy plane. However, when we move to higher dimensions, we may not find that this single integral as a valuable tool. So I am now going to take you to the double integral, and we will see what are all the ways in which double integrals can be evaluated, and then we will have a series of problems, illustrations, and as we solve these problems, we will see what are all the concepts involved in evaluation of these double integrals. So let's begin a small lecture on the double integral. Okay friends, now let me take you to a double integral. This is a typical representation of a double integral in Cartesian coordinates. So we can call this simply a Cartesian double integral. Here f of xy is a given function. Geometrically it represents a surface, and dA happens to be an area element of this particular region R. That is, so dA can be visualized as the area of an infinitesimally small rectangular area. So one can easily understand the geometry. If f of xy represents a surface, and if you multiply that with the area element, then you are actually calculating the volume of a cylinder standing on this small elementary area. So when you integrate over the entire thing, one of the interpretations is this represents volume. So the interpretation if z is equal to f of xy represents a surface over a planar region R, then double integral f of xy dA over R represents the volume under z is equal to f of xy with respect to the region R as base. So this region R will be on the base, and then you have a surface on top, and you are trying to find out the volume of that solid. Not necessarily a cylinder, but it is a combination or a collection of several infinitely many rectangular solids which are nothing but cuboids. So this sum total will give us the double integral, and as I told you, if f of xy happens to be a surface equation, then we are evaluating the volume. Now what happens in other cases? Suppose f of xy happens to be the density of or the density function of that solid, then the double integral gives us mass. So as I told you, it all depends upon the interpretation of f of xy. So two things we are discussing straight away. One thing is f of xy as a surface equation, then we are in volumes. If f of xy is the density, then we are calculating the mass. And we all know how important these interpretations are, because suppose we are discussing situations in mechanics, then the density function plays an important role. Once you get mass, then there are other related calculations that we can make. For example, we can find out moments of inertia and radius of gyration and things like that. So it is very, very essential to understand the importance of multiple integrals, and specifically it is very, very useful in electromagnetic field theory, in thermodynamics, and as I told you just now, in lots of situations in engineering mechanics and strength of materials. So let's get into some concepts, but before that I would like to show you one illustration. Varieties of ways in which we have to approach double integrals, but first I would like to show you a small illustration. Suppose we have to evaluate integral 0 to 2, integral 0 to 4, x plus 2y dy dx. Now let us look at this problem. Now the order of integration specified here is dy first and then dx, but one must not be carried away by this order unless we have understood the limits of integration. Here the limits of integration are all constants, in which case one must understand that the region of integration is a rectangle or a square. In this case, you can see that the variable y has got limits 0 to 4. So these are limits for y. So these are limits for x. So you can easily see now that x varies from 0 to 2, x is equal to 0 to x is equal to 2, then y is equal to 0 to y is equal to 4. So as you can see that whenever limits are constants, then we are integrating over rectangular regions. As the limits here are not constant, then we can find that the region is no more a rectangle or a square. We'll come to that situation in the next example. So this integration is straightforward. You first integrate with respect to y, then with respect to x. So let's do the evaluation. So let me call the required answer as I, 0 to 2 on the variable x, xy plus y square from 0 to 4 dx. The integration of 2y is 2y square by 2, therefore it's y square. So it is 0 to 2. Apply the limits for y, so you get 4x plus 16 dx. So the integration of 4x is 2x squared plus 16x from 0 to 2. So this is straightforward. This becomes 8 plus 32, and therefore the answer is 40. So this is plain double integrals. Well, we know that we are preparing ourselves for major competitive examinations to enter top institutions, either for higher studies or for selection into scientist positions. Obviously, nobody will test you at this level, but this can be a starting point by which those who have lost their fundamentals in double integrals can get back once again. So I'm now going to take you to a second problem where the limits may not be constant throughout. In my second example, I have a problem like this: 0 to 1, 0 to 1 minus x, x square plus y squared, dx dy. Suppose this is to be evaluated. Now please observe this integral, and you find that you don't have constants in both the limits. When you have a function of x here, then you must change this order in the reverse direction, dy dx. So when you have functions of x here, these represents the limits for y and these represent limits for x. All of us know there are geometrical reasons for that. So therefore the first integration will be with respect to y and then with respect to x. So let's evaluate this. 0 to 1, first integration with respect to y, x squared y plus y cubed by 3 from 0 to 1 minus x dx. So let's apply the limits. 0 to 1, x squared into 1 minus x plus 1 minus x whole cube by 3 dx. Lower limit produces nothing. So when you integrate this, you get x cubed by 3 minus x power 4 by 4, and this can be directly integrated without expansion. You will get minus of 1 minus x whole to the power of 4 by 12, 0 to 1. So integration of 1 minus x whole cube will be 1 minus x whole to the power of 4 by 4, and we should not ignore this minus sign. So therefore it has to be taken. So when you apply the limits, let us see what we get. So with x is equal to 1, we get 1 by 3 minus 1 by 4 minus 0 minus of, now the lower limit, x is 0, so you get 0 minus 0, and when you put x is equal to 0 here, you get minus 1 by 12. So it is 1 by 3 minus 1 by 4 plus 1 by 12. So let's see. You get 4 minus 3 plus 1. So this is nothing but 1 by 6. So this is how you must be very, very watchful about limits and then decide this order. Similarly, when you have functions of y here, the correct order would be dx dy and not dy dx. Once the limits are constants, you strictly follow the order which is given. Once the inner limits are functions of x, use dy dx. Once the inner limits are functions of y, use dx dy as the order of integration. Now I am going to take you to some typical situations where you need more analysis. Okay. Well friends, suppose there is a problem in double integration and we are not given the limits of integration. Okay. But the description of the region is given. This means the region which is bounded by certain curves and lines is completely described. That is, the equations of the lines and curves bounding the region are specified. Let me explain through this example. Suppose the problem is to evaluate double integral 2x plus 3y dA given R as the region enclosed by y is equal to x squared and y is equal to x. This is the situation. So now the student should know basic analytical geometry to first determine what this region is. Now all of us know y is equal to x square stands for a vertical parabola and y is equal to x is a straight line through the origin inclined at 45 degrees to x axis. So this is y is equal to x squared and then this is y is equal to x. So the region of integration is that shaded portion. So we can find the boundary points, both of them intersect at the origin and at 1, 1. Now describing this region is very important. There are several techniques. One of them says the region is spread from 0 to 1, so x varies from 0 to 1 and then y varies from this lower curve to that upper curve. So y is equal to x square happens to be the lower limit of integration and this happens to be the upper limit of integration. So the limits of integration will be 0 to 1, x square to x. This is the function 2x plus 3y and the order will be dy dx. This is how you can fix the limits of integration. Of course, evaluation is a very small job now. We completely understand. So we can also do this problem in the other way, that is in such a way that the order of integration becomes dx dy, but then the reversal of limits will take place. So if that were to happen, let me tell you how that should be understood. Second way, imagine y is varying from 0 to 1. What about x? This will be the lower boundary for x and that will be the upper boundary of x. So you will write this equation as x is equal to y, that forms the lower boundary, and x is equal to square root of y as the upper boundary. So x is equal to y to x is equal to square root of y. So if you proceed this way, then this is how you would be evaluating the double integral. Please observe that there is a complete change in the structure of the limits. So here we are making the inner limits of integration as functions of x. Here we are making the inner limits of integration as a functions of y. Both of them produce exactly the same result. The student can try and confirm so that you are practicing both the things together. Now let me take you to a very important concept after this. Friends, I want to introduce a very interesting aspect of double integrals that is very important in analyzing the nature of the region. Now this discussion is about analyzing regions in the Cartesian plane, that is on the xy plane. It is very important to understand this because the fixation of limits will ultimately decide the output. If we make errors in the limit structure, then the answers may go wrong. So therefore, I want to teach you two very important aspects. One is the classification of a region as an Rx region, and then I will tell you what is an Ry region. Both of them will be followed by suitable examples. Now imagine this is a region which is enclosed between two curves. Of course, in the simplistic case, we discuss only two curves, but when we come to advanced examples, it need not be necessarily about two curves. It can be two or more curves also, right? Now, suppose this is for this region, this is the leftmost point and this is the rightmost point. I'll just give them simple names L and R. Now we will find the coordinates of these points x1, y1, x2, y2 by solving the equations of these two curves. Now, if you imagine vertical lines through the leftmost and the rightmost points, we will observe in this diagram that between these two lines, the upper curve and the lower curve do not intersect anywhere in between. So to repeat, between this frame at L and R, the leftmost and rightmost points, if you draw vertical lines and you find that the upper curve and the lower curve do not intersect, then the region is called an Rx region. So this region can be called an Rx region. So to put it in words, R is called Rx if the upper and lower curves between the vertical lines, that is very important, drawn through L and R do not intersect. That's exactly what's happening. So this is upper curve and this is lower curve. Now the next step is you write the equations of these two things. Now because the equations of the curves are always given in the problem, we can write the lower curve as y is equal to alpha x and the upper curve as y is equal to beta x. So now you can see the limits of integration for x will be x1 to x2 and the lower limit of y is this and the upper limit of y is that. So when you actually fix the limits, it is integral x1 to x2 and then alpha x to beta x function of xy, and now we know the order has to be dy dx. So this is a very simple way of knowing the limits of integration when the region has been classified as an Rx region. I am now going to give you a simple example of a region which is Rx, and this will be followed by an example where you will suddenly find the region cannot be called Rx. So that will motivate us to define the next region called the RY region. So now let me show you a problem on an Rx region. Let us look at this example. Evaluate double integral over R, okay, f of xy dx dy, where f of xy is equal to 1, R is the region in the xy plane bounded by y is equal to x squared and y is equal to root x. Suppose this is the problem. Here both are parabolas. We can draw a simple diagram. Y is equal to x squared is this vertical parabola, and y is equal to root x is the same as y square is equal to x, so it will be a horizontal parabola. So the region of integration is that part. So now what I'll do is I will draw this region magnified so that we can analyze. This region is the same as this region. Now the points of intersection are 0, 0 and 1, 1 because both will satisfy both the equations. So I'll call this the leftmost point, I'll call this the rightmost point, and then I will draw vertical lines. You will find that between these two vertical lines, the upper curve and the lower curve are not intersecting anywhere in between. Therefore, this region is an Rx region. So I will call this Rx. So what are the limits of integration now? Rx region. First x limits, then y limits. X limits are from 0 to 1. Y limits, this is the lower limit, this is the upper limit. So what is this curve? That is the same as this curve. So its equation is y is equal to x squared. And this curve is y square is equal to x. So you can write this as y is equal to square root of x. So y is equal to x square to root x. So this is a clear Rx region. So I is equal to integral 0 to 1 integral x square to root x 1 dy dx. 1 because the function has been given equal to 1. Let us evaluate this. When you evaluate this, the integration of dy is y from x square to root x. So this will give us 0 to 1 root x minus x square. they are very, very easy to evaluate. So let me show you the calculation here. I is equal to square root of x. When you integrate, you get 2 by 3 x to the power of 3 by 2 minus x cube by 3 from 0 to 1. So this will be 2 by 3 minus 1 by 3. So the value of integral is 1 by 3. So once you have a region like this and you have said it is an Rx region, integration is only a small technical issue. Any student can do with some minimum integration practice. But what happens when the region does not permit us to call it an Rx region? So my next example should tell you how you must think in a different way when the region is not an Rx region. So friends, now let me take you to a problem. The problem is almost like the last question, but I am changing the region bounded by y is equal to x, y is equal to 2x and y is equal to 2. Right. Now here we have 3 straight lines, so obviously the region which is formed will be a triangle. So the region y is equal to x, let us say, is like this. So the slope of this line is 1, the angle of inclination with x axis is 45 degrees. Now y is equal to 2x has got higher slope, so it may look like this. So this is y is equal to 2x. Its slope is 2. Naturally, the angle is more than 45 degrees. And then we have got y is equal to 2. Y is equal to 2 is a line parallel to x axis. So this is the region of integration. Okay. Now let us find out the corner points. Origin, and then this point will have coordinates 2, 2, because y is equal to 2 and y is equal to x will intersect at 2, 2. At this point will have the coordinates, when y is 2, x will be 1, it will be 1, 2. So this is a triangle with coordinates 0, 0, 1, 2, 2, 2. Now for this region, this is the leftmost point and this is the rightmost point. So if you draw vertical lines here, we have a problem. Between these two vertical lines, there is an intersection. According to the definition of the Rx region, such an intersection is not permitted. Therefore, this region is not an Rx region. Is not an Rx. So I am going to tell you now the second type of region known as the RY region, and we will see how this problem or this region can be seen as an RY region so that integration can be easily performed. What happens if we stick to this format? Because there is one intersection between the leftmost and the rightmost point, you may have to split this into two smaller parts and perform two double integrations and then add up. So more double integration means more time consumption. Therefore, if we can see the same region as an RY region, the computation becomes lesser. So let us see what is an RY region. Okay friends, in an RY region, we have to basically visualize a situation like this. So there are two curves enclosing a region. Now this region has got this point as the bottommost point, therefore I am calling it as B, and this point as a topmost point. Remember, in an Rx region we were calling leftmost and rightmost. Now in Ry we call it bottommost and topmost. So you will find the coordinates of these points x1, y1, x2, y2. You can find them because the equations are given to you. Now what we do is we draw horizontal lines between B and T. So within this frame we observe these two curves. We are observing for any points of intersection between these two parallels. You find that this and this do not intersect. Therefore, this region is called Ry. So R is called Ry if the left curve and the right curve do not intersect between horizontal lines drawn through B and T. So this is the left curve, this is the right curve. So as long as between these two parallels the left curve and the right curve do not intersect, then the region is called an Ry region. So now I will take you back to the previous problem and tell you how easily you can evaluate that as a single double integral, provided you see the region as an Ry region. So let's go back to the previous problem. The previous problem is f of xy is 1, R bounded by y is equal to x, y is equal to 2x, y is equal to 2. So this is y is equal to x, this is y is equal to 2x, and y is equal to 2. So this is the region of integration. The intersection points 0, 0, 2, 2, 1, 2. Now for this region, this is the bottommost point. Then what is the topmost point? There are 2 points on the top at the same level. So both of them can be called topmost points. Both qualify, become the topmost points because they are on the same line. So between these two parallels, between this parallel and this parallel, this left curve and this right curve are not intersecting. Therefore, this region is Ry. So let us write the limits. First write y limits, then write x limits. It's very clear. For an Rx region, you first write x limits. For Ry region, you first write y limits. Remember, for Rx region, x limits will be constants. For Ry region, y limits will be constants. So y limits will be constant. How do we fix that? This is the lower limit of y, and this or that will become the upper limit of y. So y varies from 0 to 2. X limits will come from the left curve and the right curve. this will be the lower limit of integration and this will become the upper limit of integration. Now the equation of this line is here. So you write x is equal to y by 2 to x is equal to y. So 0 to 2, y by 2 to y, the function is 1. Now the order is dx dy. So let's find this answer, 0 to 2, x from y by 2 to y dy. So this will be y minus y by 2, so we'll get y by 2 dy. So this will be nothing but y square by 4 from 0 to 2, and you can see the answer is 1 unit. Dear friends, if you observe carefully, this will be the area of this triangle. For students who have practiced coordinate geometry, then you can easily find the area of a triangle from the coordinates, and you will find that you will get the same output. Now, how do we know the answer that we got in this problem represents area? Well, that is the very interesting part about double integrals. Whenever f of xy happens to be 1, you are evaluating the area of the lamina. So in the previous example too, you can confirm what we have found is the area of the lamina. So rest assured that whenever f of xy is equal to 1, the double integration produces area of the lamina. The only care is how quickly we can double integrate. Quick double integration means not breaking up the region. So if you do not want to break up the region, then you must know the Rx and Ry concepts. That is going to be extremely useful, and the next concept that I am going to take up is called changing the order of integration, which requires thorough understanding of Rx and Ry regions. Okay friends, these are the three main concepts or special concepts under double integration. The first one is called changing the order of integration. The second is called changing into plane polar coordinates. And the third one is about using transformations by which we can change the variables. In fact, in the second and third cases, the concept of Jacobian comes into play. But the first one is only with respect to Rx, Ry regions. So let me begin with the first concept, changing the order of integration. Well, here the problem is this can be the actual problem. Now, changing order of integration sometimes become necessary because you cannot start the integration at all, as you will see in some of the examples I am going to teach you. So this technique is generally used whenever you cannot initiate the integration. That is, you find the dy dx order or the dx dy order not suitable for the first operation. So if you change the order, a dy dx may become dx dy and integration may start. Similarly, the second case also may happen. So the general idea is to convert this into another double integral like that. So if you cannot do this, you somehow transform like this. If you cannot do this, you somehow transform like this. Sometimes an Rx region may not be a single Ry region. It may become a sum of two or more than two Ry regions. But that may become necessary because we want to integrate. Similarly, an Ry region may not correspond to a single Rx region, and it may have to be broken into 2 or 3 parts. So it all depends upon the geometry of the region. Now let me explain to you an example by which we can understand this concept. Change the order of integration to evaluate integral 0 to infinity, integral x to infinity, e power minus 2y by y dy dx. Let us look at this problem. Now this is the function, and to integrate this with respect to y, we have no methods available. So this tells us that the order dy dx for this problem is not suitable. If the order was reversed, then integration of e power minus 2 by y with respect to x is possible, because this would remain a constant during integration. So you can easily make out that for this function with respect to y, integration cannot start. So this is a strong reason why we must change the order of integration. But how do we start? First, the region should be analyzed. Analyze the region. This is the first step. So you can see these will be y limits and these are x limits. So x limits will be 0 to infinity, y limits will be x to infinity. Now let us first create the region for this one. X is equal to 0 corresponds to y axis. X is equal to infinity can be considered as a line at infinity. Y is equal to x is a straight line passing through origin, and y is equal to infinity will be like that. So the region of integration is between x is equal to 0 to infinity, y is equal to x to y is equal to infinity. So it is the upper triangle. Now this region is Rx. Now the same Rx region should be converted into an Ry region. So step number 2, visualize Rx as Ry. For that, you must imagine this is the bottommost point and these are the topmost points. So y limits first, then x limits. Y varies from 0 to infinity and x varies from x is equal to 0 to x is equal to y, because this is the leftmost curve and that is the rightmost curve. This will form the lower boundary, this will form the upper boundary. Third, So the first step is analyze the region. We have analyzed the region to be Rx. Second step, we visualize Rx as Ry. That part is over. Now write the transformed integral. Transformed integral. So integral 0 to infinity, integral 0 to y, e power minus 2y by y, and the order is dx dy. So let me show you this evaluation here. I is equal to integral 0 to infinity e power minus 2y by y into x. Integral of dx is x, 0 to y dy. So this will be 0 to infinity e power minus 2y by y into y dy. So this is gone, and you'll have e power minus 2y by minus 2 from 0 to infinity. So you can easily see the answer will be 1 by 2. Now what was not possible here, we could not even start the integration, but by changing the order of integration, the answer can be easily evaluated. So that is the greatest advantage of converting Rx region into Ry or Ry region into Rx. This is the concept of changing order of integration. Okay friends, I will now take you to transforming a Cartesian double integral into a polar double integral. Sometimes we may have a problem and the region is bounded by a polar curve. Example, circle. Circle is one of the simplest polar curves. So when you have a situation like this, then we think of polar coordinates. So what you do is, using x is equal to r cos theta, y is equal to r sin theta, these are transformation equations from Cartesian to plane polar coordinates. So you find the Jacobian, which is dou xy by dou r theta, and you will find the Jacobian is equal to r. This means dx dy, which is the area element will be now proportional to r dr d theta. This will be the area element in the polar system. This is the area element in the Cartesian system. So therefore, you will convert this Cartesian double integral into a polar double integral using this information, and then integrate with respect to r and theta as limits. So the xy system is being taken away and we are moving to the r theta coordinate system. Therefore, double integral f of xy dx dy over r will correspond to some g of r theta into r dr d theta over r. So this is the idea behind polar double integrals. However, it is not always necessary that the region should be bounded by circles. there can be other situations where the transformations may become necessary. So that means the concept of Jacobian continues to be important whenever you want to change the variables. But this is one of the easiest application of the change of variables to polar, because the Jacobian is very simple, easy to remember. The only care we must take is integration with respect to the new limits, and that is where you must visualize the region very carefully before fixing the limits. Now I am going to take you and tell you how different problems can be solved under different conditions. What is required is tremendous observational power. You must observe the limits, you must observe the region, and you must find the shortest way by which you can evaluate double integrals. So some of them may be straightforward, some of them may require changing order of integration, some of them may require changing to polar coordinates, some of them may require writing our own transformation equations so that the variables are changed, and it is in these last two cases, that is polar and changing the variables, you must not forget the concept of Jacobian. So let us begin an exercise.